In this video, we will investigate how we can use all of these calculus techniques that we've investigated in previous sections to sketch curves. Now, in terms of sketching curves, there's a few steps here that we want to follow through. Given the function, we want to think about the following bits of information. What is its domain? I.e., can we easily look at the function and think of some values that are not in the domain? Is it symmetric? Test for symmetry. Is it even or odd? Find the intercepts. That would be both the x-intercepts and the y-intercepts. If there are any asymptotes present, vertical or horizontal, we would like to find those. We would like to find the critical points, determine intervals of increase, decrease. Use that information to classify the critical points. Then find the intervals of concavity. Plot a few key points as necessary, and then sketch the graph. So a lot of information here. Let's just see how we put this all into action. So let's use the curve sketching guidelines to sketch the graph of the curve y equals x to the fourth plus 4x cubed. So our function is a polynomial, which means that its domain is going to be all real numbers, so minus infinity to infinity. In terms of symmetry, our function we would think of as being f of x is x to the fourth plus 4x cubed. So it's a polynomial with both a even term and an odd term, which means it's going to have no symmetry present. So no symmetry. Then we go on and we think about finding intercepts. To find the x-intercepts, we take our function and we set it equal to 0. So both terms have an x cubed in common, leaving us an x plus 4. So x equals 0, x equals minus 4. So our x-intercepts will be the points 0, 0, and minus 4, 0. Then we think about finding the y-intercepts as well. So to find the y-intercepts, we know f of 0 is 0. So our y-intercept is really just the x-intercept 0, 0 that we already had. Because it's a polynomial function, there are no asymptotes, but we will see an example in a previous video that does have asymptotes. And now on to the more calculus-specific portions. We need to think about intervals of increase, decrease, and classifying the critical points. So f prime x is equal to 4x cubed minus 12x squared. So to find the critical points, we need to solve for where this is equal to 0. Each term involves a 4 and an x squared, which leaves an x minus 3 left over. So we have critical points at x equals 0 and x equals 3. And what we would like to determine are the intervals of increase and decrease. So we think 3 possible intervals. What would the sign of f prime be? Well, thinking about, and I just realized I had a tiny typo here. When I took the derivative, this should have been plus 12x squared, so plus 3. And the critical points are 0 and minus 3. So the critical point on the left, let's change that to a minus 3, and the critical point on the right, we'll call that 0. So we need to think, how is f prime behaving? Well, looking at 4x squared, that's always positive, so it's really the x plus 3. If x is to the left of minus 3, that's a negative quantity. If x is to the right of minus 3 anywhere, that is a positive quantity. So we have determined here the intervals of increase and the intervals of decrease. So we are decreasing from minus infinity to minus 3. and we're increasing from -3 to 0 and 0 to infinity. And we can also classify our two critical points from this information. So looking at what happens at -3, our function is going from decreasing to increasing. So x minus 3 is a local min. And x equals 0 is not a local max or local min because the first derivative does not change sign there. The next thing to think about would be the second derivative so that we can find intervals of concavity. So f double prime x is equal to 12x squared plus 24x, and we need to determine where is this equal to 0. So both terms contain a 12 and an x, and when we factor that out, we're left with an x plus 2. So we have x is 0 or x is minus 2. So we make a number line and think about the sign of f prime. So minus 2 and 0, and the sign of f double prime. So if I plug an input to the left of minus 2, so think you plug in minus 3, you would have a negative times a negative, which is a positive. If I plug in something between minus 2 and 0, think minus 1, you would have a negative times a positive, which is a negative. And if I plug in something to the right of 0, think positive 1, you would have a positive times a positive, which is a positive. So putting this information together, we are concave up on minus infinity to minus 2 and 0 to infinity. And we are concave down from minus 2 to 0. And at this point, we've gathered all of the relevant data that we are going to use to sketch the curve. So let me just kind of recap here because I know there's a lot going on. We have found the domain. Noted in this case there is no symmetry. Found the x-intercepts and the y-intercepts. Noted that there are no asymptotes. That took care of more of the algebra-specific portions. Now it's on to the calculus. We found critical points at 0 and minus 3, the intervals of increase, decrease, and we use those to classify the critical point minus 3 as a local minimum, and 0 is neither. Found the second derivative, and used that to determine the intervals of concavity. So I've encoded all of the relevant information here that I can. I've labeled on the graph the two x-intercepts we have. We noted that minus 3 is corresponding to a local minimum, so I went ahead and evaluated the function at minus 3 to get myself a nice point that I can sketch. And we should always figure out what the points are corresponding to local maxes and mins. And now I just need to go ahead and piece everything together. So to the left of minus 4, our function is concave up and it decreases down to our critical point at minus 3. So concave up and decreasing. And once it gets to minus 3, it remains concave up until it gets to minus 2, and it's now increasing throughout. So concave up and increasing, and right at minus 2, we switch from concave up to concave down. We are concave down until we get to our point, this x-intercept at 0, 0, and we continue to increase, and we are now concave up. So here is a fairly accurate sketch of what the graph of our function will look like. Notice that in this case, because of the values that we are dealing with, the x and the y axes do not have the same scale. So I've labeled and indicated here exactly what each dash on the x-axis represents, but I've labeled the point minus 3, minus 27 to see that the scale is not the same.